Very good. Welcome back. So today we are going on with the recognition principle. And let me recall, yesterday we proved actually the main technical step in this. We proved that if you have M, an infinity space, which I recall you is the same thing as a monoid in the infinity category of spaces, then the map from M to omega of its classifying space is an equivalence, if and only if M is an infinity group. In one direction is obvious, omega of anything is an infinity group. So if that map is an equivalence, then M sure as hell is an infinity group. Sorry, an E1 group, not infinity. And the other is a consequence of the descent property for colimits. It really is a consequence of the descent property of colimits. It's not something you can just wave around. Okay. Also, I have a correction to say. Last time someone asked me about Siegel spaces, and I misunderstood the question at the time, and I don't want to enter into the details, but for the record, Siegel spaces are the equivalent thing of category objects. So you have a Siegel space, you basically have an object that is going to be like, oh, sorry, maybe I should call it X bracket 0, which is like a space of objects, and X brackets 1, and that's a space of morphisms, and then you have maps picking the identity morphisms and picking like the source and the target of your morphism, and plus higher compatibilities. And the fact that my definition of associative monoid resembles this is just a classical fact that a category can be identified with a monoid with one object. Sorry, a monoid can be identified with a category with one object in sets. That's like the higher categorical version of that. So sorry for the confusion last time. Just wanted to give the correct answer on record. So, okay. Okay. So last time we proved this fact that you can loop and take B. Yeah, yes? Was there a question? Perhaps not? Okay. So, okay, last time we proved this fact that M goes to omega B. M is an equivalence if and only if pi 0 of M is a group. And there are two missing pieces of the...
Did we prove it for E infinity or for E1?
For E1, for E1, oh, thank you very much, E1 type. I'm thinking already to E infinity today, since it's what we're going to talk most of the time today, so I made that type for E1 space. And there are two missing pieces of the recognition theorem. Remember, there are two facts. The first is that Bm is connected for every M. And the second, related to this, that B omega X is the inclusion of the connected component of the base point. So both of these are easy now. Let me say first one, Bm is connected. Well, remember that Bm is just the colimit for T in delta op of M of T. I want to study the pi note of Bm. The pi note of Bm, well, remember that pi note is a left adjoint, though. So it commutes with all colimits. So let me write it, and then I'll explain why. Because pi note is the left adjoint of the inclusion set into space. So it commutes with all colimits, and now this colimit is colimit computed in sets. But now, if you look at this diagram, what is this diagram? Pi 0 of M. So we have pi 0 of M bracket 0. Well, that's just a point. We have two maps here, pi 0 of M1, which is whatever it is, etc. And now if you look at how we compute colimits in sets, this turns out that pi 0 of Bm is a quotient of pi 0 of m of 0. Because there is a map. So for every t in delta op, you can find some map 0 into t, just pick whichever element of t you want. And then if you look at it, you look at your compute colimits in set, you make the disjoint union and you identify all the points of the sets. And so this, and also there is a map t going to 0. In fact, you can actually show exactly what this relation is exactly. But it's not very important. Okay, for a general geometricalization is more important, but here it's not really important what this equivalence relation is. In this case, it's generated by pi 0 of m. In fact, pi 0 of Bm, you can write it as the co-equalizer of pi 0 of m of 1 with these two maps, pi 0 of m of 0. That's a general fact for colimits of geometricalization of sets. You can see that every element, every class of every element always has a representative on the 0 level, and every identification factors through 1. That's because for any 2 points in T, you can find a map from 1 that picks them. Clear. But okay, but then therefore pi 0 of Bm is just the point, because it's a quotient of the point in sets. So this was easy. So that's step 1. And step 2, remember, we need to show that B omega x going to x is the inclusion of the connected component. Now, it's clear, the image is clearly contained there because B, this guy is connected. So it factors through the connected component of the base point. If you have a connected space and you map it, a connected pointed space, and you map it to some other pointed space, it has to land in the connected component of the base point. So it's enough to show that this map is iso on pi I for all I greater or equal than 1. Or equivalently, this map, omega b omega x to omega x, is an equivalence. Because pi I omega x is pi I plus 1 x. And I don't have to care about other base points because I'm looking only at the connected component of the base point. But by the triangular identities, we have omega x goes to omega b omega x goes to omega x, and we have the identity of omega x. And now this omega x is group-like. So this map is an equivalence by the main theorem we proved last time. And so we are done. As I said, it was the proposition I proved last time and actually was doing most of the work. The rest is kind of formal, playing with the relation between the various objects. Is it clear how this works? Are there questions? No. So let me sum up. So we have an adjunction monoid in spaces, pointed spaces omega, such that the image of B is in connected spaces. The image of omega is in groups. And B omega restricts to an equivalence. Okay, that's the main result that we have. That's what I call the recognition principle for loop spaces. Okay, and let me put a quick remark that I did last time, as I did already last time. This implies that omega B from E1 spaces to E1 groups is the left adjoint of the inclusion. That is the localization into the reflective subcategory of groups, and it's called group completion. And we write it as M goes to M group, and it's going to be the protagonist, I think, of next lecture. But for now, let me go on and just put as an exercise. So it's in 2 steps. You need the first one to do the second. So pi0 from commutative monoid in spaces into, sorry, not commutative, monoids in spaces to monoids in sets is the left adjoint to the inclusion. Of discrete monoids into E1 spaces. And using this, you can prove that pi0 of the group completion is the group obtained by inverting formally all elements in pi0 of M. This is just 2 is just 1 plus using the fact that the composition of left adjoints is the left adjoint of the composition. But I leave the details to you as an exercise. But I'm saying this exercise because there is a very important remark here. Even if M is discrete, sorry, I keep putting C, but it's not a given that the group completion is discrete. In fact, the functor from monoids and sets into monoids and spaces and then group complete. So that sends every discrete monoid to its group completion as an infinity space is essentially surjective. That is, any E1 group, no matter how crazy its homotopy is, can be realized as the group completion of a discrete monoid. This is a theorem of MacDuff. I put the precise reference in the notes. MacDuff, 1979. I put the precise reference in the notes if you want. And there is a fun little example of a discrete monoid whose classifying space is S2. I'll have to check the details to see if it's doable to give it to you as an exercise, but you can really get whatever you want. Okay. Questions about this? No. It's a bit surprising, honestly. We will see. Oh, we won't see. I'm not sure, but we. Oh no, we will see. Actually, yes, that when M is commutative, or even much weaker than commutative, this doesn't happen. Actually, the group completion of a discrete commutative monoid is going to still be discrete. Or more generally, when we have the Ore condition, if you've ever seen this thing in the context of localization of rings, it's exactly the same condition. That's not a complete coincidence. I'm not sure if I will be able to speak about the group completion theorem in full generality. We'll see in a couple of weeks. No, in a week, I guess, in a week or so. I'll certainly state the group completion theorem, even if I don't prove it. Okay. So that's it for E1 spaces. It's time to go back to spectra and commutative monoids. Do you have questions about what's been done so far before I very slightly change topic? No. Okay. So let's go to why are we doing, I mean, this is still supposed to be a stable homotopy theory class. So let's try to show a little bit why we spend so much time on associative monoid. So, commutative monoids. Okay, so here we are going to use fin star is the category of pointed finite sets. And we will often write an object of fin star as I plus, where I is the set of non-base point elements. Which I'll sometimes call probably the underlying set of I plus. Because secretly what I want to work is the category of finite sets and partially defined maps, but it turns out to be equivalent to the finite pointed sets. So, okay, and we will write, for example, for brevity, n plus will be the finite pointed sets whose underlying set has n elements. Now, for every I in the underlying set, there exists a map chi I from I plus to the singleton plus, sending I to I and everything else to the base point. This is called the characteristic map. Characteristic map. Okay, so that's enough combinatorics. Hopefully this is clear because now it's time to get the definition of a commutative monoid. So let C be an infinity category with finite products. A commutative monoid in C is a functor M from fin star to C such that it satisfies the Siegel condition. So for every I plus in fin star, the map from M of I plus to the product M plus, which is given by the product of chi I, is an equivalence. So that's called the Seagull condition. And I might not have said it, but even the associative monoid analog was called the Seagull condition. Okay. So let me give a remark. So there exists a functor delta op into thin star sending T to gap T plus. So the pointed set with underlined set is the set of gaps, infinite order sets, and maps. Sorry. So here we have a map from S to T. I need to send it to an F upper star from gap T plus to gap S plus, and this sends a gap, sorry, T prime to the gap in S whose image contains this gap, if there is one, and the base point otherwise. So that's formally this is the supreme, the maximum for S is less than F of T. No, sorry. Maximum for sorry, of F of S is less than T, and the minimum from T prime is less of F of S prime if max and min exist and the base point otherwise. So concretely, I have my, I don't know, 1, 2, 3, and this goes to 0, 1, 2, and this goes by sending 0, 1, 2 like this. For example, suppose I have this map. So remember, I have the set of gaps that I'm going to call 1, 2, 3 here, and 1, 2 here. So now I have 1, 2, 3, and the base point, 1, 2, the base point. Well, the base point has to go to the base point. That's forced. Sorry, goes the other direction. So 0, 1 is not in the image of any gap. So this also goes to the base point. But 1, 2 is in the image of the second gap. And so this goes to 2. And that's how the F upper star works. And notice that gap n plus is exactly n plus with the bijection that I just described. And G I upper star is exactly chi I. So GI was this inclusion of the gap. This is sent exactly to the characteristic morphism. Because, for example, what is this? G upper, GI up, for example, let me see. Sorry. Again, 1, 2, 3. So we have G1. G1 sends 0 to, no, so let's do the G2 actually, it might be clearer. G2 sends 0 to 1 and 1 to 2. And now we have 1, the base point, 1, 2, 3. And well, 1 is not in the image of any gap, so it gets sent here to the base point, and the same is for 3. but 2 is exactly on the image of the unique gap in 1, so it's sent to 1. So let me call this functor actually gap plus, because that's what it does. And so if M is a commutative monoid in C, M composed with gap class is a monoid in C, because the Siegel conditions stay the same, and that's the underlying monoid. Of our commutative monoid. And okay, all these, well, because we were going to need this thing a little bit, but the first notion is that C is an ordinary category. I mean, just a nerve of a normal category with finite products. Then I have this functor from commutative monoid into monoid, which remember we proved was equivalent to classical monoids, which are objects with a multiplication and a unit. Then this is fully faithful with essential image those monoids for which the multiplication composed with the twist is the multiplication from C up to C. If you want the monoid that are literally commutative. So twist is here, the map here that exchanges the two coordinates. So if you want, equationally, you can write it as, xy is equal to yx. So really commutative monoids. And let me actually give you a big red warning. If C is not one category, the map C mon C into mon C is not fully faithful. That's what happens when you start to include the higher homotopical structures. Being commutative now is a structure you put on your object. So let me give you an example of this phenomenon, which is concrete enough. Example/exercise if you have really a lot of patience. I did it once. I'm probably never going to do it again. So let's see the cat, the infinity category of categories. If you want the full subcategory of infinity category spanned by the nerves of categories, or if you want the simplicial nerve of the Cannon-Ridged category of categories, where you take, as a mapping space, the nerve of the groupoid of functors and natural isomorphisms. Then a monoid in C is exactly the nerve of monoidal categories and monoidal functors. Commutative monoids in C is the nerve of symmetric monoidal categories and symmetric monoidal functors. And the isomorphism is a bit tricky to describe, but essentially you need to describe what the free monoidal category and the free symmetric monoidal category on n object is, which is not hard. It's in fact just finite sets with a map to the set n for the symmetric monoidal one, and for the monoidal one, finite sets with a map to an order set. No, sorry, finite sets with a map to n and an ordering on every fiber. You can do it. It's this example actually goes under the name MacLane coherence theorem. sometimes. And that it's sometimes stated as in a monoidal or a symmetric monoidal category, all diagrams that ought to commute. And this is exactly what this combinatorial of delta or of thin star is telling you. And here you can see that the forgetful functor that forgets the symmetry is not fully faithful. It's an additional data. You have to add this symmetrizator in the definition of a symmetric monoidal category. But okay, for the purposes of this course, and I suggest forever in your life, you should take this as a definition of monoidal or symmetric monoidal category, because it's a lot easier to remember and it's going to make your life so much easier. It certainly works for me. I can never remember the classical definition of symmetric monoidal category, but this definition, I can say it in my sleep. So these sometimes are called unbiased symmetric monoidal categories because I'm not making an explicit choice. I'm just throwing all possible diagrams and all possible coherences I want at once, but they're packaged in these combinatorics of finite pointed sets. So you don't have to remember them. You just have to remember what a finite pointed set is. Okay. But let me say something about the proof of this proposition. I'm not sure. Let me copy the text of the proposition. Actually. Paste. Let me not do the full details, but so the first is that the image lands in the subcategory of the commutative things, and that's clear because, let's see. So mu now is going to be given by, as this composition. If you unwrap what it does, there is, sorry, I need 1 plus. Oh, yeah, let me first say that gap in n is n plus. I think I already said it, but let me repeat it. And then mu is given by this. Inverse chi1 times chi2, and 2 plus, and this m1 plus, which I'm going to call m of mu again, where mu now is the map from 2 to 1 plus. Well, what you expect probably is this map, sending the 2 points to the same point if you want to multiply them together, and then the base point to the base point. And now the point is that here you have a m of twist, m of 1 plus times m of 1 plus. You can write a neat commutative diagram like this. And this is the mu again, and so this is telling you that mu of the twist. And this secretly is coming from the fact that this map mu, if you compose it with sigma, which is the map exchanging 1 and 2, gives you mu again. If you exchange 1 and 2, this map mu doesn't care. So the image lies in the promised subcategory. This shouldn't be very surprising, but, and this mu in fact is, if you want, m up a star, where m was this map from 1 to 2 that I used to get the multiplication the other time. So that's why this multiplication is the m of mu. Okay. Is this clear? I'll give you some time so that you convince yourself that this diagram actually commutes. Okay. And now, okay, that's one direction. And then the other direction, I'm going to give you an inverse from that subcategory to. So remember, to give the inverse, we used, last time we used these maps and n-fold multiplications from m to, yeah, m to the t to m, where t was, when t was in delta, yeah, was a finite totally ordered set. But now I'm going to claim that in the case of a commutative monoid, the order on T doesn't matter for this multiplication because of the commutativity. So I'm going to erase the totally order. So T now is just going to be a finite set. And now if I have this M nu eta, classical commutative monoid, I can get such an object just by sending I plus to m to the I, and a map f from I plus to j plus to the following. So m to the I can write it as the product for all j in j of m of the preimage of j times actually m to the preimage of the base point, which I'm going to happily ignore. And then this is going to be sent to the product for j in j of m to the j, which of m, which is m to the j, and this is just the product of this multiplication for f to the j. It's exactly the same formula I gave you last time, actually, but written in this context. And of course, in order to do that, I need a multiplication for a finite set, not only finite ordered set. So that's why we need commutativity now. And okay, and then it's easy to check. This is an inverse. I'll leave the details to you, but well, one direction is tautological, and the other is just the fact that a map of commutative modulo, it's an isomorphism, it's an equivalence, sorry, if and only if it's an equivalence on the underlying objects, because all the other objects can be identified by the Siegel conditions with products. And so, okay. Questions about this? No. Okay, good. Now the category of commutative monoids is much better than the category of monoids, actually. And let me show a lemma that's going to be useful. A couple of lemmas. First one, this lemma here. So let's see, be an infinity category with finite products. Then this category of commutative monoids. Oh, I didn't say this is the subcategory of the functor category spanned by commutative monoids. So it's has a zero object and direct sums. So the coproduct and the product coincide. So that's what's called a semi-additive category, infinity category. And then proof, well, okay, it clearly has finite products because, okay, with a similar proof, to the case of spectra, limits are computed pointwise. That's because finite products commute with limits, as in spectra we use that loop space commutes with limits. And in fact, the proof works also for, in general, for shifted colimits, also commute pointwise with the same proof of spectra, but okay. I don't want to do the detail, I only care about the case of limits where it's obvious, because you just check that the limit pointwise still satisfies the Siegel condition. And that's because limits commute with products. Okay, but let's see that it has a zero object. So we have to take the terminal object as better be the zero object, and we need to show its initial. So we need to show that maps in commutative monoids from the constant functor, the terminal object, to M is still contractible. Okay, this is just a map in the functor category, the space of natural transformation. And now note that this is a constant functor. So you can use the universal property of the colimit to say that this is the same thing as a map in C from the terminal object to the colimit I plus M of I plus. Because functors out of the constant functor are the same thing as functors into the colimit, if the colimit exists. Actually, this is true only if the colimit exists, which I'm not assuming, but it is true because fin star has a zero object. So colimits over fin star as just computed by evaluating at the zero object. 0 plus. And that's just the point, because that's also the terminal object again. If you write it down concretely what it means, it's fairly clear what it is going to be. And this proof, by the way, works also for monoids. Also, monoids have a zero object. Is it clear? Okay, good. Direct sums are slightly trickier. Basically, we need to prove that the map, sorry, I should say where this map takes place. Is an equivalence for any M, N, and P. And where these maps are precomposition with the maps like this. And how do we do that? Well, the trick is that there is a natural transformation mu P from P times P into P such that such that these two diagram commute. And the third thing, we need that mu of p times p prime is just mu of p times mu p prime. These things are homotopic. And actually the homotopy will become natural in p and p prime, but we won't need it. It's just, we need that there exists some homotopy. Why is that? Well, because with this map, we can construct an inverse. Which concretely sends, you have f from m to p, g from n to p, and concretely it sends them, if you want, on their sum. And the three relations I wrote above, plus the naturality of mu p, shows that this is in fact an inverse of the previous map. You have the one direction is fairly straightforward. The other is slightly trickier, but essentially you need to write the following commutative diagram. How does it work? Oh, sorry, I forgot. There is another relation I'm going to need. Mu p composed with a twist is homotopic to mu p. That I'm going to need for the diagram I'm about to write. So you have m times n times n, which I can write as m times star times star times n, goes to m times n times m times n. Ooh, why did I put it so low? And I have mu m times n. Here, the identity and this commute. That's the diagram you need, and this follows from relation 2 and 3, I believe. 1, 2, 3, 4. You have to put all things together, and this gives you it gives you the hard part of the composition. That's because you can homotopy these to m times m times m times n, mu m times mu n. And then you use the symmetry too. You use the symmetry actually because I'm secretly exchanging the two ends here. So this gives you that the composition, let's see, from map m times n into p to maps m times p and p, and then back here is the identity. If you write down what this composition does, it's exactly pre-composing your map with this composition here. And so it's going to be the identity. And the other is easier. The other is pre-composing your pair of maps with these two arrows here. Okay, so the only trick is how do I construct this mu p? And mu p is actually surprisingly easy to construct because p times p of I plus is the same thing as p of I plus times p of I plus. But that's the same thing as p of I plus wedge I plus by the Siegel conditions. And this mu p is just pre-composition with the fold map from I plus wedge I plus to I plus. That sends, on each summand is the identity. Id, wedge, id. And this satisfies all the naturality and diagrams that we want to do, because it's just pre-composition. It happens, so everything in the source. Everything is happening in the source. So that's actually a slightly trickier proof that commutative monoid satisfies direct sums. If you unwrap it, if you try to write down the proof in the one categorical case, you will write down something very similar to this. In particular, you will write down this diagram here. You'll find out that this diagram is actually something you will be using. And in fact, the upshot is that in infinity categorical case, you have just to write down the same diagrams and you have just to add different words afterwards. But the ideas are basically the same. Okay. So that's, well, okay, so far I've proven that commutative monoids have direct sums. These might seem a bit weird, but in fact it's nothing, hopefully it's not something surprising. Hopefully you knew it in the one categorical case that commutative monoids have direct sums. If you didn't, well, now you know. And okay. So let me give us a definition. Let me use a definition / remark. Let M a commutative monoid and C, then Bm, which is just a classifying space of its underlying monoid, has a canonical commutative monoid structure. And the functor B from commutative monoids and C to commutative monoids and C is the suspension functor, by which I mean it's literally the push out of this thing. And okay, so there are various ways of doing this. Let me first define you the canonical symmetric commutative monoid structure on Bm, and then we'll see that this is literally given by the suspension. So Bm, now I need to give you a functor. So remember, Bm was defined as the colimit over T in delta op of the if you want, the underlying monoid in T, which I'm going to write of M of gap T plus. Because remember, the underlying monoid is just precomposing with this gap plus. And so Bm as a commutative monoid is just a functor sending I plus to the colimit delta op of M of I plus wedge gap T plus. And you can check that this satisfies still the Siegel conditions. Because let's say colimits over delta op respects products in spaces, well, everywhere, in every Cartesian closed category. So this is okay, this might be a bit surprising at first. The classifying space of a commutative monoid is a commutative monoid, but this shouldn't be a surprising fact because, for example, who is BZ? So it's a space, it's a connected space whose loop space is Z. Does anyone know, by any chance, a space whose loop space is discrete? Is the discrete abelian group Z? And a space whose pi1 is Z?
The circle?
Yes, exactly. That's, of course, the circle. By our recognition principle, it has to be this. And in fact, if you write down the equivalence, it's this. And the circle happens to have a commutative monoid structure as well, given by the multiplication. In fact, you can check, and I will check in a second that it is this thing. And actually, let me also remind that this is also Bn. Also notice that this is also Bn. And I'll give a direct proof of this fact. And the proof is, well, S1 has a cell structure like this. In particular, you can realize it as, if you want, think of the geometricalization of this simplicial set here, where I take an interval and I just identify the two borders. And this means that this is the geometricalization of the following simplicial set. How does it work? No, I am silly. It has only one cell. No. Oof. Sorry. Well, okay, let me write it. What do I want to say? Oh, I mean, okay, what I want to say is that the colimit over T in delta of gap T plus. So why is this exactly the simplicial set? And the point is that T to gap T plus is exactly the simplicial set. Delta 1, not border of delta 1. And okay, I'm trying to write it, but if the way you think about it is, if you have a gap, T less than T prime, you can think of it as the map from delta n to delta 1 that sends, sorry, from, a gap, say, in n. You can think of this as the map that sends T prime n to 1, sorry, and 0 T to 0. And this gives, in fact, this bijection of simplicial sets. And okay, this has not really much to do with S1 being Bn. I mean, it has secretly to do, but actually this is the statement I wanted to use. And this secretly, if you want, this S1 is colimit delta 1, delta 1 n is the Baus-Filkam formula. We saw, I forgot to mention, to notice it, but if a consequence of the Baus-Filkam formula is that we have a simplicial set X, the homotopical limit of X as a simplicial set is exactly sign of the geometricalization. Okay. Why am I saying this? Because I still have to promise you that that this is the suspension, and okay, so the claim is that the suspension of an object M in any category can be written as the colimit, sorry, in any pointed category. You need a zero object, otherwise this doesn't make sense, for T in delta up of T wedge, gap T plus, wedge M. And that's because, again, you apply the Baus-Filkam formula to the proof. Apply the Baus-Filkam formula to the push out. sigma m. And reinterpret using this bijection that I gave you here. This term as this term is secretly and disjoint gap T, cardinality of gap T, disjoint unions of M. Well, wedges, I guess I should say, since I'm in a pointed category, but understand what I mean, coproducts. And using, and now, so the suspension from commutative monoid in C to commutative monoids in C is given exactly by the same formula as Bm, because the coproduct is given by the product, as we shown before. Okay, sorry, this came a little messier than I wanted to, but let me deduce the existence of a certain functor now out of this. Because finally I want to reintroduce spectra. So I want to have a functor B infinity from the commutative monoid of C into space, into spectra. And this is going to send an infinity space M to the following spectrum. Here. These are the equivalents given by the recognition theorem for commutative monoids. For associative monoids, the recognition theorem for loop spaces. Where Bm is just B of B of B M n times, which now I can iterate. So this looks sort of like the formula for the suspension spectrum. It's not a coincidence. It is another variant of the suspension spectrum when you have a commutative monoid structure, but it has an advantage that at least from when you do B at least once, you have an equivalence here. Oh, I forgot to mention, why do I have an equivalence? Why is this space group-like? It's group-like. Sorry, why is this space group-like? This is group-like because connected. Because remember, we saw that B of anything is connected, in particular, if it's a monoid, it's group-like. And that's why I have to put n greater or equal than 1. For n0, this doesn't work. But you remember, we can define spectra starting from whichever point we want. In fact, let me put as a remark, omega infinity B infinity of M is omega Bm, which is exactly the group completion of M. So I have a spectrum from commutative monoid into spectra, and now let's get its little brother, its right adjoint, that goes from spectra to commutative monoid. So definition, you have omega infinity from spectra to commutative monoids. I probably should have defined this earlier because this is easier. You have E, and you send it in a functor that sends I plus to omega infinity of sigma infinity I plus tensor E. And the fact that spectra have direct sums implies that this satisfies the Siegel conditions. Maybe we should verify it by hand in this case. And so I have this guy, sorry, and I map it via the characteristic maps, but this is just you know, omega infinity definitely commutes with products. And this is a, so this is a direct sum. Because omega infinity commutes with product, since it's a right adjoint. Okay, but now the direct products are also finite coproducts because spectra has direct sums. So, and sigma infinity commutes, and tensor and sigma infinity commutes with finite coproducts because they're left adjoint. So this is sigma infinity blank tensor E left adjoint. And so concretely, this map is induced by the map, by this map, which is an equivalence, as an isomorphism in finite pointed sets. So it satisfies the Siegel conditions. As you see, the only thing we've used in here actually is that spectra has finite direct sums, and that omega infinity commutes with products. Okay, yes, I'm going to call this functor omega infinity from spectra to commutative monoids. If you want, what I've shown is that omega infinity of any spectrum has a canonical infinity space structure. And moreover, let me also remark pi 0 of omega infinity of E. And there is a subtle point that I'm going to address in just in a second, but this is just pi 0 of E is a group. So this, in fact, lends into group-like and lends into infinity groups. And what is the subtle problem that someone should notice by now? What I said is not quite a proof. Well, I didn't show you that the two group structures on pi 0 are the same. The two monoid structures on pi 0 are the same. I show it has a commutative monoid structure and it has a commutative group structure. But if I don't show you they are the same, how can I say this is a group? Okay, I'm going to address it right now, but and I think it's going to be the last thing I'm going to do today. But before that, other questions? No. Okay. So the following lemma, actually I was tempted to do it in the previous section on E1 spaces because it's completely about E1 spaces. But let me say, so that's M a monoid spaces, an E1 space. Then omega M has two monoid structures. One that's coming because it's omega of a space. One by concatenation. And the other by just sending T to omega of M of T, if you want pointwise product. And if you remember, last semester we saw indeed that at least at the level of pi notes, these two structures are the same, which is actually all that we need to say that omega infinity lends in groups, but and they are naturally isomorphic, naturally equivalent. But now I'm going to show a slightly small variant of the Ekman-Hilton argument to show that they are indeed the same, even at the level of E1 spaces. And okay, proof. Remember that the concatenation of loops was given by omega m sends t to the limit of the following diagram where these points are in bijection with gap t. So this was a limit over gap t of this functor that I called m1t, which sends every gap to a point to a point and the cone point to m to the space. So I'm going to let me call this omega m of 1 actually, to distinguish between the two, omega m and omega m of 1 with the two monoid structures. And the idea is I'm going to construct a third space that maps to both of them by equivalences. And the guy is the following, since t to the limit of this staircase diagram that I have m0, m1, m0, m1, m0, m0, where the m0s are still in bijections with the gaps of t. And why am I considering this diagram? Because if you look at this portion here of the diagram, the limit of this portion is exactly m of 1 to the gap t. Sorry, in bijection with gap t plus. Forgot that. Forgot the plus. No, sorry. I'm sorry. Sometimes I get the combinatorics wrong. It was in bijection with t, not with gap t. But it's the m1s that are in bijections with gap t. So it is exactly m, which is canonically equivalent to m of n. So if I compute the limit first by taking the limit of this subdiagram, this limit is equivalent just to omega m of n, m of t, as I wanted. But on the other hand, I can compute this limit also in a different way. That gives me this omega m1. And that's because this y clearly has a map to, sorry, receives, it has a map to, yeah, y is obtained, y of t is clearly obtained by, what do I want to say here? No, sorry. Omega m1 of t is just the limit of no, okay, that's what I want to say. I want to say m1t, this functor for which the limit is omega m1 of t, is just obtained by this diagram here by precomposition with the map from this staircase diagram that collapses all the corners of the staircase. And I claim this map is co-initial. So it induces an equivalence on limits. And that's, well, okay, this map is co-initial, i.e. it induces equivalence on limits. And that's just to apply one of the standard criterion for co-initiality. This follows from what's known as the equivalent theorem A, since everything is a poset, so you can just verify. And or alternatively, actually, you don't even need the co-initiality statement because you know that y of t is just m of t. Sorry, I was supposed to add t here. And this map to the limit is, omega m of t. And this map to the limit is just to the product of omega m of 1's over all gaps. And this is an equivalence because omega respects product. Yeah, that's probably better than saying that it's co-initial, sorry. The map on limits is this map here. So we have constructed a zigzag of equivalences between these two loop structure, these two composition, the pointwise composition of loops and the classical composition of loops. And indeed they are the same, so that's. And so this particularly implies that the multiplication on pi 0 of omega infinity e is the same as in pi 0 of e. So it is indeed a group. And okay, I don't really want to go further with this. Let me just state a proposition that I think I'm going to prove next time, that there are maps omega infinity, b infinity, and b infinity, omega infinity 1, making b infinity, omega infinity into an adjunction. That I think I did already too many diagrammatic arguments today to go with this one as well. And actually, once we have that, you will see that the recognition principle will just follow from the sky almost, from the one for loop spaces. So maybe actually let me state this and the theorem. So again, we have, what was it? M goes to omega infinity, b infinity of m is an equivalence if and only if M is a group. B infinity M is connective, by which I mean pi I. B infinity of M is 0 for all I less than 0. And the map B infinity omega infinity E into E is an equivalence if and only if E is connective. And that's the recognition principle for connective spectra. And okay, this is the theorem that I'm going to prove next time using this proposition above. This actually, other than proposition, I should really call it lemma. Sorry, I tend to call everything proposition, but that's really more of a lemma. And it's just a fairly easy and straightforward argument. And as a corollary, let me just say the corollary of this, since I announced it, there exists a fully faithful embedding of abelian groups into spectra, sending A to H of A. And that's because, well, okay, proof. It's just the composition abelian groups, which is just groups, objects in sets, this falls fully faithfully in E1 groups, and this via B infinity fits in spectra. You can in fact check that the decomposition is the factor that we described already. I mean, the nth space of B infinity A is KAN, because you can just check the homotopy groups. And it has to have the correct homotopy groups.
Is there a relation between this recognition principle and the relation between simplicial abelian groups and chain complexes?
Yes and no. You are right. There is a similar thing. And the point is, if instead of, so we have this category commutative monoids and spaces group-like, but you could have a different candidate for what it means to be a topological group in spaces. You can take group objects in topological spaces and invert the weak equivalences. Right? Instead of taking group objects after inverting weak equivalences, you can invert them afterwards. And actually, or if you want simplicial abelian, or you can put Kan complexes here, or even simplicial sets, it doesn't matter. You get the same thing for formal reasons. And it turns out that these things are different, though. And the relation you describe is exactly that this is the same thing as the connective element in the derived category of Z. So what you get is you take non-negative chain complexes and invert the quasi-iso. This is actually easier because there is an equivalence before inverting that sends quasi-iso to weak equivalences. That's called the Dold-Kan isomorphism. But this in particular tells you that you have a map from the derived category to spectra, to connective spectra. And in fact, by formal reasons, this extends easily to the derived category, of course, not to non-connective spectra. And this functor is the functor that I gave you as an exercise to construct. Actually, it's called generalized Allenby-MacLane functor. This is not fully faithful anymore, though. It's kind of a miracle that the restriction to abelian groups is fully faithful, to be honest. And there is a very big difference between them. So there is a relation in the sense that there is this functor making the diagram commute. And oh, of course, sorry, I forgot. There is, of course, these are not equal, but there is, of course, a map like this. That just, and we will see soon, I think next Monday, an example of a guy that's here, but that's definitely not here, which is in fact going to be topological K-theory. And that's what sometimes people mean when we say that spectra are not Z-linear. The some cohomology theories just doesn't take Z-linear values. And the algebraic K-theory is not Z-linear, and by which we mean exactly that it doesn't come from this guy, because actually secretly, and I really wish I had time to prove this result, but I won't. I'll mention it later maybe. But this is secretly just the category of modules of Hz over Hz in spectra. That's a Schwede-Shipley reconstruction, Morita theory, Morita equivalence. But unfortunately, I won't have time to prove it because I need to define what modules are and etc. And we will perhaps do it, mention it later when we have more things. But it's a cute result, and so okay. So that's the point when we say that if you want to work with certain cohomology theories, you have to work with non-Z linear material. You have to go below Z. so to speak, so over the sphere spectrum. That's exactly what we mean, that some stuff lands here and cannot be factored through this guy. Particular topological K-theory, you might ask, oh, is there a chain complex whose homotopy groups are, homology groups are topological K-theory groups? And the answer is no, because the K-theory lands here and it doesn't have a Z module structure. It doesn't lift through this. I don't know if this was the answer you were looking for, but and for those that have never seen the derived category, sorry, that's an important, but that's actually a very important thing, that you inverting and taking group objects does not commute. Inverting weak equivalence and taking group objects does not commute, and you get very, very different theories. And if you think about it, this is because you get a Z module structure on every, abelian group, of course. Because what is weird is that if you take actual group objects, not necessarily abelian, you do get the same thing as as spaces. But that's a very special situation. That's sort of a coincidence. This is the same, actually this works also in other settings. For example, this is the famous structification theorem that tells you that if you have a monoidal category, you can realize it as a group object in the one category of categories. Sorry, in a monoid object in the one category of categories. You can structify monoidal categories. You cannot structify symmetric monoidal categories, and the reason is exactly the same as the failure of these. Somehow associativity conditions are easier to force, commutativity get a lot hairier. And yeah. Okay. And on some levels, a lot of work is actually reducing to this Z-linear situation that's easier to understand than spectrum. Like you typically try to find filtrations on your cohomology theory whose associated graded is going to be Z-linear. That's a whole story, because it's easier to manipulate. Sort of a lot of work is in, let's try to understand these in terms of these, because this is easier. Yeah, the idea here is about spectral sequences, of course, the prototypical example of this. But okay, I think I've overstepped my time. So unless there are other questions. No, okay, let me stop the recording.